All right. Sorry about the little error with the AM PM thing, but fortunately you let me know, so I was able to fix it and only killed us about a couple minutes. So let's go on talk about the quiz. So let me share my desktop. Okay, so here's the quiz. And the first question is, determine if the following series converge or diverge. Show your work and state the test you're using. Okay, and the first one is the summation of cosine squared of n over n cubed. So we want to look at it and say, well, what does that kind of look like? What nice, easy series does that look like?
1 over n.
1 over n? Maybe a little bit, but not quite. Yeah, 1 over n cubed. 1 over n cubed. The problem with 1 over n is that 1 over n and 1 over n cubed behave very differently. Remember, 1 over n diverges, 1 over n cubed converges. So you got to be careful because this is closer to 1 over n cubed. Okay, the other thing to note is that the cosine, and I've actually copied it over here, the cosine is always less than or equal to 1. And by squaring it, I've made sure everything's positive. There's no problem with that. So what we can say is that the, the cosine squared of n over n cubed is always less than 1 over n cubed. Do you all agree with that? Because if the cosine's less than 1, the numerator on the left is less than the numerator on the right, and the denominators are the same. So I can make this inequality, and actually technically it's not less than, it's less than or equal to, actually is less than, I don't want to even go there, but less than or equal to is all we need. All right, well, and we know that the sum, and let me just copy this sum, and make that a 1 on the top. So we know that the sum of 1 over n cubed, does that converge or diverge?
That converges.
Yeah, converges. And as I mentioned, you always have to state the test you're using.
It's p-series test.
Yeah, by the p-series test. I'll just write PST. Any questions on that? All right, so if we have a convergent series and we have another series that's always where all the terms are less than your convergent series, what test can I use? Yeah, the comparison test. I'll say CT. So by the comparison test, the series that we're interested in, this guy, also converges. Any questions on part A? Any questions? Okay, let's go to part B. Okay, so we look at part B and we say, well, on part B, what's the dominant term in the denominator? Okay, yeah, the dominant term in the denominator is n. N gets large really fast. Root n gets large slower. So what I want to do is I'm going to compare it with 1 over n. Okay, you compare it with 2 over n, but 1 over n is good enough. So let's compare it with 1 over n. Well, there's a bit of an issue. But let me just write it out. So let's copy and paste it in and then adjust. So let's get rid of what we don't want. Okay, and by the way, does this converge or diverge? You better all know.
Diverge.
Yeah, and why does it diverge?
The harmonic series test.
By the harmonic series test, which is a test for one very special series. But have you noticed it just keeps coming up all over the place? Okay, in fact, it's going to come up again in this section we're going to talk about today. So that diverges by the harmonic series test. All right, well, here's if we could look at this and we could say, well, that denominator is n plus root n. The denominator is actually bigger than the denominator of 1 over n. So that means the items are not smaller like we need them to be. Sorry, they all are smaller, they're not bigger. So we're not able to use the comparison test. But what test can we use?
The limit comparison. It's
Exactly. This one has to be done with the limit comparison test because the inequality is backwards. And when the inequality is backwards, you can't just use the comparison test, you have to use the limit comparison test. So now let's find the limit. So we're going to have, and I don't think I mentioned it. I think I mentioned it briefly last time, but I didn't do it. And that is, I typically skip the step because we're dividing, right? We're looking at the limit of the quotient, right?
yes.
Of an over bn. When you divide, you multiply by the reciprocal. Hopefully you all know that. And it's always fractions in this game. So I'm just going to do that all at once, if that's okay with y'all. And when I do that, I'm going to get 2n over n plus root n. Let's write that out. So we're going to take the limit, and I'm just going to assume n goes to infinity, and then of 2n over n plus the square root of n. Okay, now how do I take that limit?
Plug
First,
in
you
infinity.
simplify out the n. Oh,
Yeah, you could do that too.
Yeah, we could plug in infinity and you'll get infinity over infinity, which means we have to do work. Does that make sense? We could divide, I think the easiest way is to divide top and bottom by n. So just do algebra in this case. And we get 2 over 1 plus, and we have root n over n, which is 1 over the square root of n. Any questions on that? Okay, what is that limit?
2.
2. Okay, so let's save this in, because that was the work we needed. Okay, why is it important the limit is 2? How does that help us?
We know it converges.
Yeah, that was
Two,
number
yeah.
1. And remember, number 1 is the main one. You're just almost always going to get a nice non-zero constant number if you choose good comparisons. So then we can say the series, and let me just pop this guy in, series we're interested in. diverges by the, what test?
Comparison test.
Not comparison test, the limit comparison test. I'm gonna write LCT, which is different than the comparison test. Part A was the comparison test, part B is the limit comparison test. Any questions at all on the first problem? Okay, now let's look at question 2. By the way, I need to let you know, be careful what you ask for because you might get it. Do you know why I'm saying that? I don't hear anyone telling me maybe you don't want to admit it. Oh, a couple of people asked for true falses on the quizzes, so I put one in. So hopefully you're happy that I put it in, or at least the people that asked for it. Okay, so if a and bn are both greater than 0, okay, and suppose that an and bn, the series, both converge, then the sum of an times bn also converges. Okay, so we have to decide whether we think this is true or false. What do you think?
I
I
used,
think it's true.
yeah, I was thinking it was true, and I used 1 over e to the n.
Okay, you
from
can't
our
do it by example.
Oh,
Examples don't show true because then anything most things false will also be true by example. So you got to be careful about that. So we need theorems. So what theorem can we use?
the
Here's a hint.
LCT,
What's that?
the limit comparison theorem.
You could use the limit comparison theorem. Okay. So we can use the limit comparison test. Okay. Okay. All right. So here's what you can't do. A couple of you are wanting to do this. It's so tempting. If you're trying to show it's true, you can't do it by example. And I'll show you that on part B. Okay. It doesn't work to show it by example because it doesn't tell you it's true. You have to use theorems. Okay. So we can use the limit comparison test. Okay. And that will work. So let's try it. Well, what do we want to compare with? What are we going to compare? It should be obvious. What are we can compare with the summation n equals 0 to infinity of a and bn? What are we going to compare that to?
AN or BN?
Yeah, it doesn't matter. They'll both work, right? Everything's symmetric. So let's compare. So note that, and now we got to take a limit. So we're going to take a limit of a and bn over an. So let's make that an equation. So the limit of a sub n, b sub n over a sub n. Well, you better all be able to do the basic algebra because that's the limit of b sub n. But what do we know about the limit of b sub n?
It converges.
To what? We actually know the number.
I think it's
What does it
1.
converge to? Who remembers? Let's see, y'all jumping in. It converges to 0. Remember that if a series of positive terms converge, then the limit of the terms must be 0. That was the very first test we had. Because if it's not 0, the divergence test tells you that it diverges. Does that make sense? So I'm going to write by the divergence test. Is that clear? Because if it wasn't 0, it would diverge. So now that we have that, now by the limit comparison test, the series summation A and Bn converges. So true. Any questions on that? Any questions? Okay, so now what we want to do is we want to look at part B. By the way, I want to do this because I can see a lot of you would get fooled by it. So let me read it first. If an and bn are both positive, okay, for all n, and let's suppose that the summation of an converges and the summation of bn diverges, then the summation of an over bn converges. So what's wrong with this statement? So let an equal 1 over n cubed. Okay, so we know that converges and it's all positive, right? And let bn equal 1 over n. Well, an over bn is 1 over n squared, so it converges. Notice the question marks. What's wrong with that? So what's the problem with the argument I just made? I'm telling you it's wrong. So what's wrong with it?
You can't prove true things using using examples.
Exactly. Exactly. In fact, B is false. So this is why you got to be really careful. You can never say true by example. It does not work. On the other hand, false by example is logically okay. Okay, that's part of logic, is that if you can find one example that makes it not work, then it's false. But if you can find one example that makes it work, that does not make it true. So I'm going to erase that because it's just wrong. Instead, let's come up with an example where we're going to get divergence instead of convergence. Actually, let's not erase it, because what I can do is I can just adjust it a little bit. See that? 1 over n cubed? Let's make it 1 over n squared. And let's let bn be 1 over n. Okay, what's an times bn?
1/3. 1 over n to the third, sorry.
Oh, sorry, an over bn.
Yeah, that's n divided by n squared.
And what's n divided by n squared?
1 over n.
So let's write that down. So an over bn equal 1 over n. Okay, well, what about the summation of 1 over n? Converges or diverges? You better all know. Yeah, diverges by the harmonic series test. So I'm gonna whoops. Try one more time. So therefore, the series diverges. So false. Because I found an example that made it false, and that's good enough to show false. It's not good enough to show true to find an example. Any questions on this true false question? Okay, so that's the quiz. And now it's time to move on. And we're going to get rid of that guy right there, the AN greater than 0 and BN greater than 0. Now we're going to start allowing negatives, but only a certain kind of negatives. So let me go and get into my lecture note area. So first thing is a definition. And that is the following. A series summation of AN is called an alternating series if for every n the following holds true. A sub n times A sub n plus 1 is less than 0. Let me highlight it and let you know that alternating series is what this is all about. Okay, just let you know this is it's a different wording than the book. My wording's a lot easier to write out. That's one of the reasons I did it, and it's easier to check. But it might be harder to see it's an alternating series. So I'm going to talk about how do you really tell that you have an alternating series? Okay, so when you hear the word alternating, hopefully you don't need to know math or anything. Hopefully you know what alternate means. What does alternating mean?
Usually changing direction.
Yeah, it goes back and forth, right? That's what alternating is. So in this case, it goes positive, negative, positive, negative, positive, negative, et cetera, et cetera, et cetera. It could also go negative, positive, negative, positive, negative, positive, et cetera, et cetera. That's fine also. Okay. Another way of saying that is if you multiply 2 consecutive terms, you get a negative number. Is everyone okay with that mathematically? Okay. So let me write down, note, usually, but not always, you will see the following. -1 to the n, or -1 to the n plus 1. In an alternating series. So hopefully you know that if you see a -1 to the n, it goes positive, negative, you start at 0. And similarly, if you see a -1 in the n plus 1, it goes negative, positive, positive. Have an X. There we go. Any questions on kind of the idea of what this is? Okay, there is one special alternating series. Anyone guess what that special alternating series is going to be?
-1 to the power of n over n.
Exactly. And that's the alternating harmonic series. We already saw the harmonic series was the most important divergent series. Well, there's the alternating harmonic series. And it turns out, this is just to confuse you, that's the whole point of why it's true, is that the alternating harmonic series converges. And we'll talk about that in a moment.
Of course it does.
Yeah, just to mess with your brains. Okay. All right. It's called life. Okay. So the alternating harmonic series is going to converge. So you got to be careful about, saying, I heard the word harmonic, it must diverge. Not if it's the alternating harmonic. Okay. So just a note that these things get interesting. If this were a regular, like normal class, then here's what I would do for y'all. Okay, so you can imagine, maybe you could all do it yourselves in your room that you're in right now. But unfortunately, with this kind of environment, we can't do it. Is what I do is I get out a ball. Okay, often a ping pong ball, but most balls will work. And I pick it up, I lift it up high, and I drop it. And then we watch what's going to happen. What's the motion of that ball going to do? Especially it's not carpet, that's a hint. Yeah, it's going to bounce. So it's not just going to bounce once. How many times is it going to bounce? Especially if it's a really good ping pong ball.
Many times.
Many times. Okay, so that is kind of the biggest and most important, one of the most important physics examples of an alternating series, because it goes up, or it starts going down, then it goes up, and then it goes down, then it goes up, and then it goes down. But the amount it goes up and down changes at every bounce. Can you imagine that too? And that's because whatever you've learned in physics, by the way, there is something called air resistance. That does always happen. So it doesn't go up and down forever with the same height. Do you all agree? I hope you all know that, right? And that's because of air resistance and friction. So what you end up getting is you get an alternating series where the terms themselves decrease. So the absolute values decrease as n increases. Okay, and that's a kind of a classic important physics example, because it happens a lot where you let things go, it goes back and forth and back and forth and back and forth. So that's not simple harmonic motion, Victor. Is a really good guess. And the reason why it's not simple harmonic motion is when you have simple harmonic motion, what's the assumption? And the hint is it's an assumption that never happens in the real world. Yeah, there's no friction. Okay, so I'm doing the true real world example with simple harmonic motion. That ball that you dropped and get bounced will come back up to your hand over and over again forever, and it'll never get lower. Okay, but that's not the real world. So this is true bouncing motion. Okay, where it satisfies the second law of thermodynamics. You know what that is? So I'm throwing some chemistry at you too, and physics, I guess, depending on where you learned it. And you remember the second law of thermodynamics? Sure, you've seen it, right? Maybe you haven't. Okay.
Is that where the total amount of entropy in the universe changes.
Yeah, so what it says is that when you have motion, you always lose some energy of that motion to heat, basically. Okay, and that's pretty much what's happening. And because of that, which we'll see in a moment, you get a convergent alternating series. Any questions on that idea?
The only thing that kind of bothers me is that why would it alternate from plus and minus in that sense? If we know we lose some energy.
Origin. So let's say you put your origin halfway in between your hand and the ground. Then you start with plus, right? Then you go down, so you subtract. And then you go up when it bounces back up. Do you see that?
Okay, yeah.
And then you go down when gravity takes it down. Does that make sense?
Yeah.
So it's going up and down and up and down, and every time up is positive and down is negative.
Okay,
Yeah.
that makes sense.
Yeah, so it's very basic, but you have to, understand what your axes are and stuff like that. But you've all done it. I mean, since you were probably a year old, you were playing with balls, right? I think everybody does. Okay, so anyhow, I figured I should mention that because it gives you a good sense of reality. And the next theorem basically is something that you already knew when you were a year old. And that is the ball is just going to eventually just come to rest. Is that clear? Okay, and come to rest means that there's a limit. So now let me state the big theorem. And it says the following. Okay, and it says that and let me just copy and paste. I think this is the easiest way. If the sum of an is an alternating series, such that we don't end up with a divergence test, okay? Remember, if you don't go to zero, you have no chance. Do you remember that? So such that the limit of an is zero. Is zero. So again, you have no chance if the limit's not zero. We already showed that. If the limit's not zero, it diverges in your history. Okay, so if you have an alternating series such that the limit is equal to zero, then the series converges. And let me write down so that you know what to call it. This is called the alternating series test. So it's a really easy test to apply, actually. All you have to do is make sure you have an alternating series, take a limit. If you get zero, it converges. If you don't get zero, then what do you do?
Perhaps we could try and limit comparison test.
You don't need to, that's the hint. The hint is you smile, but why do you smile?
Because then you know it diverges.
It diverges by the divergence test. Because if you don't get zero, the divergence test says it diverges. Do you remember that? So the nice thing is if you have an alternating series and you can take a limit, it's all you ever have to do to decide whether it converges or diverges. Is that nice? Sometimes taking a limit's hard, but really there's only one test when you have an alternating series. And well, there's two tests, but it's the same process. You take a limit, If you get 0, you say converges by the alternating series test. If you don't get 0, you say it diverges by the divergence test. And that's it. So let me do an example. And it's the most important example, the one I just mentioned. And that is, let's look at the sum of -1 to the n over n. Okay, and we'll start it at 1 so you don't have any problems with 0 being a problem. So first thing, this particular series has a name. And I've said it already, but I'm going to say it again. This is the alternating harmonic series. All right. Well, this is really easy. First thing is it clear this is an alternating series?
Yes.
Because negative, positive, negative, positive, negative, positive. I'm just going to assume n starts at 1. Okay, this is an alternating series. And now let's do the next really clear, easy thing. Take the limit of 1 over n. Well, if n goes to infinity, what's the limit is 1 over n?
0.
That's 0. So by the alternating series test, AST, the series converges. Any questions on that? Okay, just a note, by the way, you might be curious. We're talking about 1 plus a half, right? So we're looking at, basically we're looking at, sorry, we're looking at 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, et cetera, et cetera. Any guess on what it might converge to?
0.
That's a good guess, but it's not true. Natural log of 2. I didn't expect you all to guess that, but I figured I should tell you. Okay. In the next chapter, we're going to figure out why, but we're not ready yet. So these things, you know, these famous series, they all come from something really important called power series. And this is one of the biggies.
Isn't the natural log of 2 like 0.6 in decimal?
Something like that, yeah.
Okay.
Right, you got 1 minus a half, right? Now we're at 0.5, plus a third, which is around 0.8, right?
Mhm.
Minus a fourth, which is around 0.6. Do you see how we're getting there?
Yeah.
So at least it should feel good that natural log of 2 seems to work, you know. That's not a proof, by the way.
That's crazy.
Yeah. When you see it, you'll understand. But we're not there yet. That's next week we'll start working on it. It might be the week after that we actually get to that example, though. Remember, we haven't really used this stuff for anything. Have you noticed that? I mean, yeah, I'm saying a bouncing ball, but next week is when we start using this. We start seeing why is it that we care, and we'll see that. And it has to do with the fact that if you use a calculator or a computer, it can only do addition and multiplication. There may be buttons for other things. No. There may be a sign of X button. It's not doing sign of X. It's doing addition and multiplication. And we're going to find out it's going to do it as a power series. So that's just a big note. So that's what's coming. And so natural log is addition and multiplication as a power series. But you've got to believe me for now, and we'll get there. Any questions on this example? Okay, let me give you a quick little, I don't know if it'll be a full rigorous proof, but why this is true, because that's important too, is we have this alternating series test. Why would it converge? And the key is, so this is the, I'm just going to do in quotes, proof of the alternating series test. So what's going on here is, first thing, it doesn't really matter, but I'm just going to start, I'm going to assume the first term is positive. If it's not, by the way, just multiply the whole series by -1. Multiplying the series by -1 doesn't change whether it converges or diverges. Do you believe that? So if it's not positive, make it positive. Okay, so we're going to assume the first term is positive. Well, if the first term is positive, and let me write the first term of an. Whoa, what just happened? Not what I wanted. Did some weird stuff. Do it again. I think I hit footnote instead of equation. Okay, so let's assume the first term of a sub n is positive. Okay, then, now let's look at what s sub 2n is. Okay, that's kind of what we're going to do. We're going to look at the even sum term. So s sub 2n, well, that is going to be, well, we're going to add up all the terms until we get to that even term. So we're going to get a sub 0. I'll start at 0. You can start at 1, but I'm going to start at 0. Plus and then what we're going to do is we're going to look at a sub 1. Oh, you know what? I want 2n plus 1. I want the odd one in this case. 1, 2, just a minute. Now 2n is what I want. So it's going to be a sub 1 plus a sub 2. And then you're going to have plus, and then you're going to have a sub 3 plus a sub 4. And then we can plus some more. And then the last one will be a sub 2n minus 1 put parentheses plus a sub 2n. Any questions on that? Any questions? All right, well, we look at this and we can think, in other words, this is the sum. And we start out with a naught. And then you look at a1 plus a2. That's negative. Do you believe you? Do you believe me? And then a3 plus a4 is also negative. And so is a5 plus a6 because we're alternating. So a1 is negative, a2 is positive, A3 is negative, A4 is positive. If you take, and they're decreasing the absolute value. So A1 plus A2 will be negative. Okay, and we can keep going like that forever. So that means that S sub 2n is a decreasing. So S sub 2n is decreasing. Any questions on that? So it's a decreasing sequence. On the other hand, we can take this, and I'm just gonna copy and paste it. We also know that S sub 2n, I can just change the parentheses a little bit. And I can write that as A naught plus, plus A sub 1 and then plus A2 plus A sub 3. And we can keep going. And what you get is now we're looking at S sub 2n, and A naught plus A1 is positive, A2 plus A3 is positive, etc., etc. Do y'all agree? So what's happening is we're going to get a positive bound. So we know that this is positive, so we know this has got to be greater than 0. Any questions on that? So if you have a decreasing sequence that's always positive, what do you know?
It started off pretty high.
No, better. I'm looking for one very important special word. It converges. It's monotonic and it is bounded. Do you see that? It's bounded by 0. So therefore, the series converges. Any questions on that? Okay, you also have to, and I'm not going to do it because it takes a lot of time, but basically you do the same thing for S sub 2n plus 1 to make sure that the odd terms also converge. Is that clear? And it's the same, but you just move the parentheses in different spots. But then if we look at the difference between S sub 2n and S sub 2n plus 1, that goes to 0 because that is going to be just A sub n, or A sub 2n in this case. And that'll give you 0. So if you take S sub 2n plus 1 minus S sub 2n, you get A sub 2n plus 1, and A sub 2n plus 1 goes to 0. So that means S sub 2n and S sub 2n plus 1 are the same. They both converge, so they converge to the same thing. Okay, so I put in quotes because I'm not going through all of it, I'm just kind of saying it. But I wanted to do the kind of the important part, and the rest is just kind of redundant. Any questions at all on the alternating series test? It's really easy to use, isn't it? Do you agree? Take a limit and you're done. I want to mention something. Something I said up here is usually, oh, I should write not always, but not always, you're going to see -1 to the n and -1 to the n plus 1 in an alternating series. Where else do you see positive, negative happen? Where in your math life have you seen that kind of thing going on? where it's above the axis of the x-axis and below the x-axis and above the
Trigonometric
x-axis.
functions.
Yeah,
What's
trig
that?
functions.
Yeah,
Sine
sine
and
and
cosine
cosine.
specifically. Yeah.
Yeah, sine and cosine. So there's a lot of sine and cosine examples that are like hidden negative one to the ends. So you're going to see it there also. So that's just a note. I want to give you a little heads up that that's the other time you're going to see it. And not just any sine or cosine, it has to be just written right. I want to mention it. Most of the time it's going to be a negative one to the n or negative one to the n plus one. Okay. Any questions on that? Okay, let's do the remainder theorem. So here's the remainder theorem. It's a beautiful theorem because it's easy to remember. Let the summation of an be an alternating series. So let's put that in. Let me write a convergent alternating series. Okay. By the way, if it's divergent, you don't even care about remainder because there is no such thing as a remainder because there is no finish. You know, you take the first 100 terms, you don't say, well, I'm close to the answer because there is no answer. But if it's convergent, there is an answer. And then you want to say, well, I'm going to take the first 100 terms, let's see what I get. Okay, then the remainder when using, and I think I need to actually on this one put in a low and a high, otherwise it won't work. One more try. Not giving it to me, just a minute. Huh? I'm trying. Let's start over. Sub and let's truly start over. And equals, and it doesn't really matter that you start at 0 or 1. I'm going to start at 0 because that's going to happen a lot more later. Super infinity. Of an. And then we're going to use the summation n equals 0 to, I'm going to say capital N. As an estimate or approximation is an absolute value less than a sub n plus 1. So it's easy. I mean, that's a formula you can all remember, I hope, is if you take the first 100 terms, the arrow will be the 101st term, no more than that in absolute value. Isn't that beautiful? Okay. Let me do an example. Find the remainder, find a bound on the remainder for using n equals 0 to, let's go n equals 1. I'll make it 1 now, just for fun. Of -1 to the n over n to approximate the alternating harmonic series. And the idea is it's really easy. What is it? What's the bound on the remainder? There's like nothing to do. That's the hint. So what's the bound on the remainder? Or what's the bound on the error for the remainder is what I meant. On this error. Well, see, I'll jump in. It's supposed to be easy. That's a hint. So you use the first 1,000 terms to approximate the alternating harmonic series. How much at most are we off by? I'm sure some of you can figure this out. Any ideas? Y'all still there? All right. Maybe it's not obvious for you. 1 over 1,001. Next term. That's it. You're done. Any questions on that? Do you see how I got that? I just plugged in 1,001 because we're adding up to the thousandths term. The remainder is no more than the 1,001st term in absolute value. So the -1 in the end just goes away. Absolute value kills negatives. You just get 1 over 1,001. No one answered this. So I'm a little concerned that maybe I confused you without knowing it.
So you plugged in 1,001 because it was the next number after 1,000?
Exactly.
So is that what you do for all of these? Like for examples like these?
Yep. So now let's do one in reverse. So do you agree it was easy?
Yeah, that makes more sense.
Okay, suppose I will let you know. So given that, and this is something that you don't know, but I'm telling you now, and we'll learn later why. E, and it's the E that you know, the E to the X E is equal to, and by the way, this is one you're going to memorize eventually, just not today. It's a summation of, oh, you know what? I can't do E, sorry. E to the -1 is what I have to do. Okay, or 1 over E is equal to the summation of fraction -1 to the n over n factorial. Okay, I'm sure you're all like thinking that, right? Okay. So approximate E. I guess I should say how many terms do you need to approximate E to E to the -1, sorry. to 2 decimal places of accuracy. Any questions on the question? Okay, now here's some math, and it's really important in science classes. What does it mean to approximate to 2 decimal places of accuracy? This is really important.
To
Huh?
round to 2 decimal places.
But what does it mean to approximate it to have 2 decimal places of accuracy?
How close you are to the accepted value given 2 decimal places.
But how close must you be? If I tell you I'm accurate to 2 decimal places, what's my maximum error?
0.01%.
Okay, so first thing, it's not gonna be a percent, right? It's just an error. The second, I had a feeling probably most of you would think it's 0.01 and it isn't. It's 0.005. So in other words, E needs to be less than 0.005. Why 0.005 instead of 0.01?
Because you can round it, rounds up.
Exactly. When you're talking about 2 decimal places of accuracy, when you're doing the rounding to the second decimal place, that comes from the 3rd decimal place. Do you remember that? So that's why, and use the rules of rounding, you know, bigger than 5 or bigger, you round up. Less than that, you round down. That's why it's a 0.005. So that's just a note. That's more of a science thing, but it's so important. I figured I should tell you guys because, you know, you don't need calculus for it, but it's an important thing. It comes up a lot. Okay. And by the way, I should say E as in the absolute value of the error. So just to let you know that. Okay, so I'm going to rewrite this because it'll make life a little easier for us. And whether you can do it in your head or not, I don't care. But I want you to believe me that 0.005 is 1/200. You good with that? It's 5/1000 and 1/200. So now we want to say what value of n is going to make this work. Now we just got to go explore. So we need to be 1/200 needs to be greater than n plus 1 factorial. Because when you take an absolute value of an, that -1 of the n goes away. You just have 1/n factorial. And then the theorem talks about an plus 1. 1 over, sorry. So now let's explore. And you may or may not know the factorials, but 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and 6 factorial is going to be more than 200, right? 720. So if we let n plus 1 equal 6, then 1/200 is greater than 1/6 factorial. So what should we let n be? Very easy, by the way. Like the easiest algebra you can believe in.
Five.
5, yeah.
Yeah, n plus 1 is 6. I hope you all know how to calculate, how to do the algebra on that. N is 5. Okay, you actually don't have to go very far at all to get a very accurate representation of 1/e. that nice? Any
Yeah.
questions on that example? All right, so now I'm going to give you some issues. I'm going to look at another example. I'm going to look at the summation.
I have a question real quick.
Sure.
Where it says let n plus 1 equals 6, then 1 over 200 is greater than, is it 1 over 6 factorial or is it 1/6 factorial?
What do you think?
I think it's
Here's the
1
end.
over
Only
6.
one of them makes any sense. The other one isn't even defined.
It's 1 over 6 factorial.
Yeah. Yeah, you can't have a fraction factorial in this class.
Okay.
Okay. And if you're not going to be a math major, you can never have a fraction factorial. Got it?
Sounds
Okay. And
good.
maybe even graduate school. I'm just not gonna ever go there. Okay, so for all of y'all, factorials have to be whole numbers. Okay. Actually, natural numbers have to be 1 and above. 1, 2, 3, 4, 5, 6, etc. Okay, I'm going to look at this little series. Just -1 to the end. Do you believe that's an alternating series?
Yes.
I'm going to start at n equals 0. And let's look at it. Well, if n is 0, what do you get?
1.
1. Plus, if n is 1, what do you get?
-1.
Plus, if n is 2, what do you get?
1.
If n is 3, what do you get?
-1.
Let's do some more just for fun, because I can copy and paste. All right, what's this first pair give you?
0.
What's the second pair give you?
0.
What's the answer?
0.
Okay, but let's do it differently, just for fun. All right, I could take the first term, which is 1. Do y'all agree? Plus, and then I could take the second and third term. -1 plus 1. Y'all agree? Then I could take the third and fourth, the fourth and fifth term. And I get -1 plus 1. And then I can take the next ones, etc., etc., etc. What do I get? I get 1 plus what?
0.
Plus?
0s for the rest of them.
Mm-hmm. What's 1 plus 0 plus 0 plus 0 plus 0 forever?
1.
1. Hey, look at that. I just have a new theorem. 0 equals 1. Y'all happy with it? What's wrong?
Which one's the real answer?
What's wrong?
0 does not equal 1.
Well, we know that. Yeah, you should worry about a theorem that says 0 equals 1, by the way. You should all worry about a theorem that says 0 equals 1. So what did I do wrong? Where's the error? What step is wrong?
I'm guessing where you start grouping.
Here's what's wrong. You're not thinking about what we've been doing the last week or so. Here's what's wrong. This is false. Since the summation -1 to the end diverges by the divergence test. We have a divergence series. You can't do things to it. Okay. So this is going to be frustrating because it doesn't feel like I did anything wrong. Right? I just added a bunch of things and I got the answer. And then I did it with a different grouping and I got an answer. You shouldn't get different answers, but you do. And the answer in this case is there is no answer to this. Okay, so this is a big warning. If the series diverges, don't touch it. Don't even try to do grouping and adding and stuff like that. It diverges. You can't do associativity. Is that clear?
Yes.
Okay, it just doesn't work. There's no allowing of grouping. It gets worse. Okay, you want to see how it gets worse? Now let's do one that does converge. Okay, what's the most famous series that converges?
One divided by n squared.
No, that's alternating.
Oh, alternating. Okay.
Alternating harmonic series. Let's look at that one. That's 1 plus, well, how about a half? Sorry, plus -1/2 plus 1/3. And then plus, and then we have -1/4 plus 1/5 plus, and then we have -1/6 plus 1/7. Oh, it didn't make it a fraction. That's interesting, but it is, etc. Okay, any questions on that? Okay, and if you do these, well, we could do it this way, but we can also look at it a little differently. We can look at it, I'm going to take, in fact, I don't even want to put the parentheses in here. I think that's just going to confuse you all. What I could do is I can say, well, that's 1. And I can look at a half, a fourth, a sixth, an eighth, all the way up, right? And just notice something. If I take a half minus a fourth minus a sixth, let's just take a look at this before I write 1. Let me just do a half plus a fourth plus a sixth. And I keep going forever. Well, what do I know about that? I can write that as 2/2. Oh, sorry, yeah, 2. I can write that as thinking about this as a half, a fourth, a sixth. And I can rewrite that a little bit and think about this. Does this converge if I write it this way?
Yes.
Why?
Because we're getting a little bit larger each time.
We're getting a little larger each time, but are we getting large? Are we getting too large? That's the question. So let's rewrite this as the following. We could rewrite this as a summation of, well, this is 1 over n times 2. Do you agree? If I pull a
Yes.
2 out of a half, I get, if I call it half, sorry, times 1/2, not 2. So it's a half of 1 over, of the summation of 1 over n. Well, that diverges, that's infinity. So in particular, I can grab all the positives, I can grab all the negatives first if I want, and I get negative infinity. Well, that's a problem if I rearrange. You see that? So if we rearrange, add all the even terms up first, we get divergence. That's a problem, isn't it? Okay, so you can't use the commutative property of addition. It gets even worse, and there's a theorem. Okay, let an let the summation of an be a convergent harmonic, I'm sorry, alternating series, and let K be any constant. Then we can rearrange the terms to get it to converge to K. So it says that if you want the alternating harmonic series to converge to 73, you can do that by just rearranging the terms, changing the order. So it tells you commutativity is just false, very false. You can't just change the order of the terms. On the other hand, if the summation of the absolute value of a sub n converges, we say that the series is absolutely convergent. And rearrangement does not change the series. So if you had, say, -1 to the n over n squared, that converges. We say it absolutely converges because if you take away the -1, you have 1 over n squared, which converges by the p-series test. And then you could switch the terms all you want, and you'll never change the answer. But if it is a series that is conditionally convergent, so if it is not absolute, if is convergent, but not absolutely convergent. We call it conditionally convergent. Let me put that in red. And this one in red. So these are definitions of absolute convergence and conditional convergence. So to show something conditionally convergent, you show the alternating series test, and then you show that if you take the absolute value, you get divergence. Okay, to show something's absolutely convergent, you take the absolute value and you show you get convergence. To show it's divergent, if it's an alternating series, you use the divergence test. So those are the three different processes. All right, so we're out of time. Sorry about that. I went a little over. That's because I got stuck because of that mistake on the AM/PM thing. I apologize. But I'm going to stop the recording.